Yes, welcome student. Welcome for today's lecture. So today we will first define one important notion, and then we will go to so two important notion we will learn today. So one is very small thing. So let me start that thing. So um, so this definition. This is lecture number 26. So let R be a unitary ring, okay, and so I'm thinking whether I need a commutative property or not. So let me just define any unitary ring. We define something called the characteristic. The characteristics of R is the least positive integer n such that n times r. N times r is what? N times r means that is r plus r plus r. We're adding r n times, okay. This is equal to 0 in R for all element R belongs to R, okay. So if you understood that, for every such elements, if this is possible, then we call this the characteristic, okay. So so you can define by another equivalent definition. I will tell you soon. So what does that mean? That means it is a least positive integer for which if you perform the addition of any element same many times, it ended up with a zero element, okay. And so one thing you should note down that okay, so let me write down. Yes. One thing you should note down that you may ask what happens if there does not exist such n, right? And then how do you define? Okay, so if so I will give example also. So if there is no such positive integer, then we say, or whatever, so we say that R has characteristic 0, okay. So this is characteristics, okay. Okay, characteristic 0. Okay, so if there exists a positive integer, then you choose the least one among those positive integers. That will be defined the characteristics. We will define that number is a characteristic of the in R. If not, then you say that 0 is a characteristic, okay. So like for example, you see that in Z, so most important, the most natural ring. In Z, you see that there does not exist any such integer, so there does not exist any n such that n into a equal to 0 for all a belongs to Z. Okay, so what do we say? We say the characteristics of Z equal to is 0. Okay, characteristics 0 ring. Okay, and this is maybe example 1, and then you can have example 2. So in example 2, I can ask you what happened to the known thing. So the known another important class of ring, say Z mod nz. Okay, with this usual addition and multiplication. This is known. So here you see that here if you just add any for any element, say a bar belongs to R, okay, you see that n times a bar equal to n a bar, which is 0 bar. Okay, and n is the these positive integers. Why? Because yeah, so yeah. Okay, I will define another way, then you will understand why n is least positive integers. Okay, so these characteristics of Z mod nz equal to n. Okay, so equivalently, what I was telling, that you can have equivalent definition. So another definition. So I mean, they are equivalent actually. So instead of for everything, if it is true for one, then you can define. Okay, so because I have started with unitary ring, you know, so one always exists. Where is that? Yes, so for unitary ring you have one, so you can define. If you don't have a unitary unit, then you will define by this way. Okay, but as I assume unitary ring, so for unitary ring, you can define that characteristics is the least positive integer n such that what happened? Such that this 1 plus 1 plus 1, if you add n many times, that becomes 0. Okay, and these two are equivalent. You can obviously prove the earlier definition is equivalent to this, and the proof is simple, because see, earlier definition you are saying that for every such element A, it has to be 0, right? If you take n many times, and in particular if 1 is there, then for 1 also this is true, right? And conversely, if this is 0 for every such n, then you can multiply, you just define your this in R is nothing but R plus R plus R plus R n many times, right? So this is 0. So anyway, so you can easily write down both ways. Okay, so these two are equivalent, right? Like you write down n into R equal to n times 1 plus 1, or rather R times 1 plus 1 plus 1 this is n times. You know this is 0, so n r equal to 0, right? Okay, so you have this property, and now question is that so if you have a special kind of ring, then can you say anything special about characteristics? For example, if you have an integral domain, okay, then what happens? Okay, so what is the characteristics of an integral domain? Okay, simple question I'm asking you. Then now you can have the simple answer also. So you see that obviously it can be 0, right? For example, r equal to z, so this is an integral domain, right? And you know the characteristics of z equal to 0, right? So it can be 0, 0 can be an option, right? Now question is that can it be a composite number? And the theorem is that characteristics of an integral domain is either 0 or prime, or some p is a prime number. Okay, it cannot be and composite number. It can be 0, obviously. If it is 0, there is nothing to prove. Okay, and now we need to check that it cannot be a composite number. So how do you check it cannot be a proof? So let say n equal to some n1 n2 n1 into n2. Okay, so n1 n2 both are greater than 1 be the characteristic of an integral domain, say R. Okay, suppose, and then we see that there must be contradiction. Okay, so what does that mean? So if n equal to this into this n1 into I must, this is a product I'm writing as a product of two prime numbers. Okay, or rather two sub numbers. So I don't know whatever. Okay, so I want to check that whether this integral domain has, integral domain means commutative integral ring. Remember, this is commutative integral ring and having no zero divisor, right? Now if this is the case, then what happens? Then we need to find out something. Okay, now in integral domain, you know that these elements now then you see that this n1 you can write down as 1 plus 1 plus 1, this n1 times. Okay, so this is an element in the integral domain R, right, as 1 belongs to R, right? Similarly, and obviously you check that this cannot be 0, right? As n is the least positive integer, right? N is the characteristic as n1 is less than n, right? And this can be possible only for n. Similarly, you have n2, which is also not equal to 0, the element of R, right? So R has two elements such that they are not equal to 0, right? But n1 into n2, which is nothing but n, that also you can write down 1 plus 1 plus dot n times, right? This becomes 0, right? As n is the characteristic of R, right? Okay, so what does that mean? That means you have two elements which are non-zero but product becomes 0. So what does that mean? That means n1 and n2 are 0, right? So that is, R contains 0 divisors, right? So which is a contradiction, because R is integral domain, which is a contradiction. Okay, because R is an integral domain, right? So in cannot be a composite number. Clear? So if what does that mean? That means it has to be prime or 0. Okay. Yeah. So maybe you can have similar thing for this what is called a field, but that we will prove later when we will discuss the proof thing. Okay, field thing. Okay, now let us discuss some new thing which we are going to discuss, the main topic of today's talk. So okay, so this thing, let me define it, called so before defining that thing, so let us define some of the exam definition. Okay, now so in this discussion, what I am assuming that my ring is a commutative integral ring. So this is at least integral domain that is given to us. Okay, and now we are going to discuss some special kind of integral domain, how this will look like. Okay, so so definition: let R be an integral domain. It is minimum we require integral domain. Okay, this is given to us, and now I will define many definitions. So definition 1, so an element R belongs to R is okay, maybe I can write down two things. So yeah, so maybe let me write down two things probably. A non-zero non-unit. I don't need this thing. Okay, this is I'm avoiding element R. So it cannot be 0, cannot be unit also, belongs to R, is said to be what? Said to be an irreducible element, or we will say only irreducible in R. What happened if you can write down R equal to something, say A into B, then either one of them must be unit. So what does that mean? Then either A is a unit or B is a unit. Okay, one of them must be a unit. Clear? So if you have such decomposition of numbers or elements into product of other two elements, then one must be an unit. Then these kind of elements are called irreducible element. Okay, and if it is not the case, if you have element A, B such that neither A and B are unit, then A is called irreducible, reducible element. Okay, and it is called reducible otherwise. Reducible otherwise. Okay, so clear. So I will come to definition example also. In fact, some example also require some idea of something called norm. Okay, that maybe we will discuss later. Okay, so irreducible elements are what? That you cannot kind of break into smaller element unless one of the product is unit. Okay, this is the meaning of irreducible. So you see, so this looks like kind of definition of prime which we learn in our school, right? And indeed, in our school, whatever the way we define primes, that is the same definition actually. What are the important things that play a role that I am going to prove today? The ring of integers has a nice property, and that property was called unique factorization property. Because of that is possible. That I am going to prove it. Okay, so this is one definition, and the definition number 2, I am going to define there is something called prime. So how do I define prime element? So similarly, a non-zero, non-unit element, say P belongs to R, is said to be a prime or prime element, whatever, if P divides say product of two elements in R. So if there are two elements A, B in R, then either P divides A or P divides B. So this is the definition in R. Inside R means, so you have element C such that A equal to P into C for this case. Okay. So see, this was not the natural definition of prime when we learn in school, right? But this is the natural definition. This is the definition of prime. Now you will understand. Okay, and the definition you learn is kind of similarly this thing. Definition number 1. This is actually defined as a irreducible element. Okay, and we require another definition. This definition. So, and then we say two elements, say some, if you have x and y belongs to R, two elements are say something called associates, are so C, okay, associates to each other if what happen, if they differ by a unit. So that means if x equal to some unit time y for some unit u. Okay, so u is the unit. So if they differ by a unit, then these elements are called associates, and they have similar features. So for example, they generate the same ideal, and the ideal generated by x, that is the ideal level, they are same. Okay, this is kind of if and only thing. Okay, so these three definitions are very much important definition required. I will discuss some of the example. For example, inside C, inside Z, so again Z, you see that you know the prime number, right? So primes inside Z, primes are irreducible. Why? I will give a proof. Okay, don't worry. Reducible. Okay. But there are examples where you have something which is I mean, obviously the converse also true, and irreducible, and conversely. Okay, means irreducible are also prime inside G. They are same actually. Okay, but in general, can you say anything about this relationship between prime numbers, primes or irreducible? And the answer is yes. For example, so let me prove this theorem, and that tells you that if you have integral domain, then primes are always irreducible. Every prime element is irreducible in an integral domain. Okay, so you need require minimum integral property to prove that primes are always irreducible, right? So primes are very special kind of irreducible elements. Okay, but the set of irreducible element can be bigger than prime number. Okay, that we will prove it. Okay, so just to prove something's irreducible, so you start with the prime number. Let P be a prime in an integral domain R. Okay, and what I need to prove, now consider P equal to AB. So what does that mean? That means I am asking that I want to check that the P is irreducible or not, and to check something irreducible, what I need to check, if it is product of two elements, then it has to be, one of them has to be unit, right? So now P equal to AB, so that is, this implies P divides AB, right? P equal to AB means P divides P, right? So this implies P divides A or P divides B, right? As P is a prime. We just defined that before. For prime numbers, if it divides something, then it has to divide one of them, either thing, right? So either P divides A or P divides B. Okay, now if with the loss of generality you assume that say P divides A, if P divides A, then what happened? Then okay, so let me write down this. So without loss of any generality, so that is WLAG, means without loss of generality. Assume that P divides A. What does I mean? I mean that you can assume that P divides B also, and same proof is true for that. Okay, so that is what, if P divides A means A equal to some P times something, say C, for some C belongs to R, right? For some C belongs to R. So what does that mean? So that means, thus what happened, you remember P equal to AB, we started, and we just now learned that P divides A means A equal to PC, means you can write down PC into B. Okay, and this implies that P times 1 minus BC equal to 0. Okay, and this implies 1 minus BC equal to 0, as R is an integral domain, and P not equal to 0, right? P is a prime number, so it cannot be 0. So and then you know that if we have product of two elements in 0, then either of one has to be 0. P cannot be 0, so it has to be 0, right? Because R cannot contain 0 by that, right? So what does that mean? That means B times C equal to 1, and this implies B is a unit, right? What I assume, you recall that I started with the P equal to AB, and then I proved that B equal to unit. So what does that mean? That means it is a irreducible element, right? Because if you write the product of two elements, one has to be unit. So thus the proof. So P is an irreducible irreducible element, or P is irreducible, whatever, right? So integral domain property is sufficient to prove that prime elements are always irreducible elements. But converse is true. So what about, so this is natural question you can ask. So what about the converse? The converse is not true actually. So not answer, not true in general. So what does that mean? That means that you can have a prime numbers set of prime. You may have something. See, primes are irreducible, right? So you may have some weird thing which are irreducible, and prime is containing primes. Okay. Okay, and so let me start with an example. So let me define this ring is called set towards a minus 5. This is what? This is all the element of the form a plus b root minus 5, where a, b are element of the integer c. Okay. And now you see that in this ring, what happened? In this ring, you have elements which are irreducible, not prime. Okay. So for example, 3, choose the element 3. 3 is and irreducible. Yeah, so why irreducible? I require some more property that I will prove later. Okay, but it is not a prime that I can prove right now. Irreducible element. Okay, but not a prime. Why it is not a prime? Now you see that 3 divides these elements, 1 plus minus 5 into 1 minus into 1 minus 5. Okay, why? Because this is nothing but 6, right? But 3 neither does not divide any of those, right? Or and yeah, this is and. Okay, so 3 is not a prime number, but believe me, 3 is a irreducible element. That I will give you proof when I use the something called norm function and equivalent domain. Okay, I will give you proof. Okay, so there are elements which are not prime numbers but irreducible numbers. Okay, so natural question then, what kind of property you need so that these two idea or these two numbers definition become equal, they are equal, right? And for that I need very important idea, and that I'm going to now discuss. This is called unique factorization domain. Factorization domain. Okay, so so let me define. So an integral domain, so minimum integral domain property is there. Integral domain R is said to be a UFD. UFD means unique factorization domain. So let me write down by this notation UFD. Otherwise, I have to write down again and again unique factorization domain. UFD if every non-zero non-unit element, say R belongs to R, can be written as product of finally many irreducible so that is what that is you can write down R in terms of say P1 P2 not some Pn. So these Pi's are irreducibles, they are irreducible. Okay, and not only that, this factorization is kind of unique, and the above factorization is unique up to associates. So what does that mean? That means that is so you can obviously you can have some more factorization, but then the element of those factorization are associated to the original factorization. That is so that is if you write down R equal to some Q1 Q2 and Qm something, then what happens? Then this first of all n has to be equal to m, and these QIs are these QIs are actually associates of PJs. Okay, so that means Q1 may be associated of P2, Q3 may be associated of P1, something like that. So that is you can write down that your this n. Okay, so your n your R you can write down that P1 P2 Pn, and also you can write down as some. So if you multiply associate means what, that P1 will be some Q3 into unit, right? So if you take all the units some unit times Q1 Q2 and Qn. Okay, this unit is the unit that coming from product of all the units, right? You can easily prove that product of units is also unit, and if you collect all the units they form a multiplicity group. Okay, so these are the properties that you can write down as kind of this factors among those things, right? Okay, so example, obviously what I was telling, that the integer ring of integers. Okay, and that's why you see that here prime numbers and irreducible numbers are same, because we are going to prove that inside UFD these are same actually. Okay, and then you have polynomial ring. So this is also UFD. You write down any polynomial in terms of product of smaller polynomials. Okay, so yeah, so these are all UFDs. Okay. Okay, so maybe you can have some more things. So maybe for a ring, if you start with any field, then also there AFD. There are more than EFD actually. These are all EFDs. Okay, I will give proof why it is more than EFD later when I will learn. We will learn something called Euclidean domain. Okay, these are all examples. Now something's not a UFD, you can give. So examples that we just discuss are Z mod. This is not an UFD. Why? If you write down that, you write down 6 equal to 2 into 3 and 1 plus 5 into, and you see these two are different factorization of 6. See these 2, 3, they neither they are associated to each other, and this is not unique also, right? So this is two distinct factorization of 6, right? So that shows that this is not unique factorization domain. So you cannot factor this thing uniquely in terms of product of irreducible primes, okay? So, and they are not associated also. So this is an example of ring which is not a unique factorization domain. And now the main important theorem here, which I am going to prove, that in unique factorization domain, the primes and irreducible are same. Okay, so proof the theorem first. In UFD, primes and irreducible are same. So irreducible are same. So what does that mean? That means a number is prime if and only irreducible, right? And conversely, like if and only if. So proof. So one part is a bit obvious, because as UFD, so in any UFD R, say let me write down, say R is the UFD, okay, as UFD is R integral domain what you have. So that means that primes are irreducible. That is obviously right, because in integral domain every prime number, every prime element is an irreducible element, right? Now conversely, let R is irreducible in R, which is an UFD. Okay. Now I need to check that R is prime number, right? Now to check, now consider that R divides something, say xy in capital R, okay? And if you have to prove R is a prime number, what I have to prove? I have to prove either R divides X or R divides Y. Then I am done, right? Okay, so this is given. So that is, then what happened? Then you can write down X to Y in terms of some R times some Z in R, right? This is definition of divisibility, right? So now, the unique factorization of R implies, so unique factorization implies what? So you can write down your X in terms of small product or irreducible. So you can write down that something is P1 P2 dot some Pn, and Y also you can write down some Q1 Q2 dot Qm, and that is equal to R times Z, right? Okay, whatever. Okay, so unique factorization, and I never said that these PIs are distinct. Even by the definition of unique factorization, I never said that the irreducible element has to be unique. They can repeat also, okay? And if they repeat, it doesn't matter. So you guys write down that they repeat together. So also you just recall that R is also irreducible element, right? So if you factor these, So R is already sitting here, right? Irreducible element, and you know that inside this factorization, these are the only irreducible element. This P1, P2, Pn, Q1, Q2, Kn, right? So what does that mean? That means R must be one of those. Okay, so that means, so that is R must be one of these PIs or QJs. Okay, one of those things. Again, without loss of any generality, assume that say R equal to something, say P1. You can choose anything, doesn't matter. Okay. Then what happened? If R equal to P1, then your X can be written as, or you see, these are, or maybe associates. So as I say that up to associates, right? So I said, so R may be associates of P1. So let me write down that R is, okay, so this line I should say differently. R is an associate of, I must say that thing because it can be associate also, associate of say P1. Okay, that you can write down R in terms of something unit time P1. Okay, or other P1 equal to unit time R, whatever, all are same. Some P1 equal to some U dash time R, because U dash is the inverse of U, right? Now that is what you can say. You write down X in terms of P1, P2 and Pn, and now inside P1 you can write down plug in R, so it is unit times R into P2 and then Pn, right? So X you can write down in terms of R and then some units. So units doesn't matter because they have the same ideal, right? The same ideal. So what does that mean? That means simple as R divides X, and this is what we require, right? So we assume that R divided XY, and then we prove the R divided X. Simple as R is a prime number, or R is a prime element. Sorry, R is a prime element. R is a prime. Okay, so this is essentially so it can be assumed that you can assume that R is anything other than P1, P2, Pn, P3, or PQ, or Q1, Q2, Qn also, right? For any case, there has to be a prime element. Okay, so now so this is the proof of very important theorem. Now I will just finish today's talk with one definition. So inside UFD you can define something called greatest common divisor, GCD. So how to define? So let you have two elements, say X and Y belongs to the UFD R UFD. So you write down X in terms of this, maybe you write down say unit times some irreducible alpha 1, and then Pn alpha n, and then Y you write down as some another unit times Q1, beta 1, and Qn, Qm, and this, or rather I don't know, I am not same QP. Okay, U dash time. Okay, so this is P1, and then writing down say beta 1, and then Pn into beta n. Okay, like these, see, these alpha i's and beta i's can be 0 also. So what does that mean? That means some of the factors P1 may not be inside X, and some of the factors say P3 may not be inside into Y also, right? So they can be 0 also. So then you define the GCD of XY is what? This is the minimum among P1, P2, whatever the common. So P1 power minimum of alpha 1, beta 1, whatever the minimum one. similarly into product of p2 power minimum of alpha 2 beta 2 and so on, and n power minimum of alpha n beta n, and you note that some of the pi's may not be exist here usually, because some of the alpha n or beta n may be 0 also, right? The minimum will be 0. So then, so by this we define the GCD here, and then we'll see that this is actually defined the GCD. When you learn maybe PID, I will define these things properly. Okay. So in EFD you can define GCD of two elements. Okay, so what we learned today? So we learned that the way we learn primes in school, they are actually definition of where is that thing? This is actually definition of irreducible element, and for prime we have a similar definition, little bit different, and these notions are not same. Okay, so in particular when you have integral domain, then primes are always irreducibles, special kind of irreducibles. The converse is not true because you have some elements which are not prime but irreducible. Okay, and then in search of the criteria, we prove that you have something called unique factorization domain. We define this, and inside that definition unique factorization domain, we just prove that prime element and irreducible elements are same. They are equal. Okay, so by this I am going to stop my lecture today. Okay, bye.